Inter-Integrated Circuit, or I2C, is a serial communication bus created by Philips Semiconductors in the early 80s. Despite its relatively low transmission speeds, it's still an incredibly popular wiring and protocol scheme used by processors to talk to various peripherals, like sensors. I'll show you how to use I2C with ESP-IDF to read data from a sensor. We'll use the inexpensive TI TMP102 temperature sensor on a breakout board for this demo. Connect power and ground, and connect SDA and SCL to GPIO5 and GPIO6 on your ESP32. The connections are the same for the Xiao ESP32S3. Note that GPIO5 and 6 correspond to D4 and D5 on the board. If you don't have the necessary hardware, don't worry. I'll show you how to use QEMU to emulate I2C. If you look at the datasheet for the TMP102 and scroll down to section 6.3, you can find a chart showing how to set the device address. If you are using the SparkFun breakout board, pin A0 is connected to ground by default, which sets the address to hex 48. Scroll down to section 6.5 and you can see that this sensor only has 4 16-bit registers. The temperature register is where we'll read the temperature reading from. The configuration register can be used to set various properties like conversion rate, shutdown or sleep mode, and interrupts from the alert pin. We'll leave these at their defaults to make this demo easier, but feel free to play around with these options by writing bits to this register. The T-low and T-high registers are used to set upper and lower thresholds that cause the alert pin to toggle if those temperatures are reached. This is great for firing an interrupt on your controller to handle such events, like shutting down or limiting a motor speed. Once again, we won't use these for this example, but know they are available on the TMP102. Scroll back up to figure 6.2. Here you can see how we should construct our message to write to a register. You first write the device address on the bus, which is hex 48. Note that this is a 7-bit address, as the final bit is reserved for telling the device that we want to write to it with the next byte. The receiver, the device in this case, acknowledges the byte by pulling the SDA line low after our microcontroller releases it. Once we see that, we can then send it the address of the register we want to talk to. As we only have 4 possible registers, only the last 2 bits matter in this byte. Once again, we make sure that the device acknowledges the message. From there, we can send out our 2 bytes to be written to the register we chose. After each byte, the device pulls the SDA line low to acknowledge reception. When we're done, the controller releases the SDA line to indicate a stop condition after the acknowledge is received. To read from a register, which is what we mostly care about in this demo, we need to send out 2 messages. The first part is the same as before. We send out the device address on the bus followed by the register address. The final 2 bits would be 00 for the temperature register. Note that the host indicates a stop condition after this. Then we send out the device address again, but notice that the read-write bit is high this time, indicating a desire to read from the device. After the device acknowledges the byte, it sends us 2 bytes from the register we requested in the first message. Scroll down to table 6.8. Notice that the temperature is 12 bits and that the final 4 bits are always 0. You can set the extended mode bit in the configuration register to set the resolution to 13 bits, but we'll leave it at the default 12 bits. Back on the first page of the datasheet, you can see that the 12-bit resolution is 0.0625 degrees Celsius per bit. With that in mind, we'll have to do a little math to convert the raw reading into degrees Celsius. If you go to the I2C API reference for ESP-IDF, you can find some great examples of how to initialize the I2C library and use it to read and write to connected devices. I2C master transmit receive will be our go-to function for reading temperature data from the sensor. Notice how the read-write sequence is the same as what we saw in the TMP102 datasheet. If you scroll down, you can read about the specific function calls available to us. A common pattern you'll see for ESP-IDF is to first initialize the bus, which includes passing in the pins you wish to use for your serial data and serial clock lines as part of this bus config struct. This will give you a handle to the bus, which you then pass to this add device function. Here is where you'll set the device address on the bus. You'll use the handle from that to call your read and write functions. For that I2C master transmit receive function, we'll need to pass in an I2C device handle, the register address we want to read from, the size of that address, a buffer to read into, how many bytes to read, and how long to wait for the communication to complete. For simplicity, we'll leave this at -1, which means to wait forever. Note the possible return values. It's common practice to check these in your code to ensure that the function executed successfully. In our workspace, go into Apps, and we're going to create a new project. We're going to call this one I2C temperature demo. And in here, let's put our main folder, and we're going to add main.c. We'll first include the standard input-output library so we can print F to the screen. We'll then include driver I2C master from ESP-IDF. This lets the ESP32 act as a controller to talk to our various devices. Then we'll include free rtos.h. We just mostly need it to delay our main thread. We'll define our I2C port. Some of the ESP32 variants have 1 or 2 ports that you can choose and then pick which pins you want to assign to those ports. Note that you can also just set this to -1 if you want to let ESP-IDF figure out which port it should use automatically, but we'll set it to port 0 for now. Then we'll select our serial data pin, or SDA. We'll set that to pin 5, as that's what we have connected to our TMP102 sensor. We'll also set our serial clock pin. This is SCL. We'll set it to pin 6. And let me make this all caps so it matches up. The I2C controller on the ESP32 has a glitch filter. Every now and then you get electrical glitches on the lines, and the controller can just ignore some of those. In this case, up to 7. This is typical where it just filters those out. This allows for better or more robust I2C communication. We will set the address for the TMP102 on the bus. In this case, it's hex 48, as we saw in the datasheet. Note that I'm going to call this TMP10X. That's because what we're going to create here is a demo for both the TMP102 and the TMP105. That is a simpler sensor, but there is a virtual version of it that's baked into QEMU that I'll show later, and the same code can talk to the TMP102 and it will talk to the TMP105. We will use that for an actual hardware demo as well as a virtual demo when using QEMU. Note that there are a few slight differences between the TMP102 and 105, so you should check the datasheet if you're actually using the physical hardware, but this simple read temperature demo just works for us for both of them. Then we'll set the serial clock speed for the I2C. In this case, we're going to use 100 kilohertz. This is the fastest it can go for standard mode. If you want to go beyond this, up to 400 kilohertz, you need to enable high speed mode, but standard mode is fine for the kinds of communication that we're doing. Then we will set our delay time so that we don't just spam the console. It waits 1,000 milliseconds between each reading of the sensor and printing that temperature to the screen. When you're creating a driver for an I2C device, you'll often list out the various register addresses, assuming that the device has registers on board, like our TMP102 and TMP105. We won't be listing all of them. In this case, we're just going to list the address of the temperature register, which is at address hex 00. Feel free to list the others, like the configuration register, if you want to try working with those. In our app main function, we will declare our ESP return variable so that we can store and check the return values from some of our functions. We'll also need a handle for the I2C bus, and we'll need a handle to the I2C device that is attached to that bus. We will create a 1-byte unsigned integer variable that holds the address of our register as we're working with the device on the bus. We'll also create a buffer. In this case, it's just 2 bytes that will hold the temperature data as we read it in off the bus. Finally, we need our 16-bit temperature variable. Note that we're just going to store our temperature in an integer format for simplicity right now. I'm not going to use a float, which means we're dropping anything after the decimal point. This is just to keep the demo simple. Feel free to try using a float, printing it to the screen to see how that works. To set up I2C communication using this bus, we're going to create a bus config struct. We're going to be using the I2C master bus config to do so. And this is a simple struct to hold the data that we will then use to initialize I2C. We will set the port number, the SDA and SCL pins. We will also attach a clock source. In this case, we're just going to use this predefined I2C CLK source default. We will set our glitch ignore filter. In this case, we're going to ignore up to 7 glitches. And then we will use the flags.enable internal pullup so that we can enable the internal pullup resistors in the ESP32 so we don't need to add external pullup resistors. Note that some of the boards, like the TMP102 board from SparkFun, might contain those pullups, so you might not need that here. If we go to definition for that struct, you can see the various options available for us. We filled in most of these, but we've left some of them blank, in which case defaults will be used, and this should still work. Then we will initialize the I2C bus. We will call this I2C new master bus function, pass it in the config and the handle for the bus that we created earlier. We will then get the return value and check it against ESP-OK to make sure it's okay. If it's not, it will throw this error to the console saying it failed to initialize the bus, and we will call this abort function, which basically exits out of this function and can stop the processor to help you debug. You can also use this ESP error check macro if you so desire. The way this is often done in the example code is the function is just called in here, like so, and it does the same thing as getting the return value, checking it against ESP-OK, and throwing an error if it's not. And in fact, inside it calls this abort function. But to be explicit, I'm going to save that return value, check it manually, and then print a customized error message to the screen. Now that we have created the I2C bus, we are going to go ahead and define our device and connect it to that bus. As we did before, we're going to create a specialized struct. In this case, it's the I2C device config struct. We will give it the device address length. This is an enum. In this case, it's a 7-bit address length. And we will set the device address. This is the hex 48 that we defined earlier as part of our static global variables. And we will set the clock speed here so that the bus knows which speed it should use to communicate with that device. Once again, we can go to the definition of this struct. You can see the various parameters that are used here. And sure enough, this device length is indeed this enum. So if we go to the definition, you only have really 2 options here, a 7-bit address length and a 10-bit address length. That's why they want you to use this enum for that particular setting. Let's go back to our code. We will then call this I2C master bus add device. This essentially creates a device on that bus, at least in software terms. We pass in the bus that we created earlier. We pass in the device configuration we just made, and we pass in the handle to the device so that we can then communicate with the device using that handle. We will once again check that return value against ESP-OK. If it's not equal to that, we'll print the custom error message to the screen and abort. Here is where we will create our super loop. I'm going to delay at the beginning of the super loop so that if there's a problem reading from the temperature, we can just go back to the top of the super loop and guarantee a delay rather than just spamming the console if there's a failure. Next, we're going to store the register address in our register buffer. You don't really need to do this because we're only working with one register right now, but note that this is a decent way to have a buffer for your register address as you're trying to write it out. This is useful if you, say, have multiple registers that you're working with in a device. Next, I'm going to call the I2C master transmit receive function. I'm going to pass it in the TMP102 device handle. Let me scroll up to make sure that that handle is spelled correctly. Looks like we're good. I will pass it in the address of that register buffer. That's the address of the register we want to talk to or read from. That is 1 byte. I'm going to pass it in our data buffer. That's 2 bytes. So we need to tell it 2 bytes. And then we will specify the timeout. -1 means wait forever. This turns this into a completely blocking function if you don't want to return from it. That's probably the easiest way to go for now. If you want to make your code more robust, it's always recommended to put in a decent timeout there and handle it appropriately if you can't read to the device or read from it. Then we will check the return value against ESP-OK. If it's not equal, print that we could not read the temperature value from the device to the console. And instead of aborting, we're going to continue, which means go back to the beginning of that loop, delay, and then try again. We're then going to convert that 12-bit temperature data that we got from the device to an actual readable temperature in degrees Celsius. We will take the first byte that we read, we will left shift it by 8 bits, and we will bitwise OR with that second byte we receive. Because the last 4 bits are 0 in that temperature data, we will right shift everything by 4 bits and then multiply that value by 0.0625 in order to get the temperature in degrees Celsius. You are welcome to modify this if you want to use floating point values to get a more precise temperature value, but for now, to keep things simple, we're just going to print this temperature that we calculated. It will be in whole degrees, and that's fine for this demo. We'll go ahead and print it to the console. Let's save, and we need to make a couple of CMakeLists files so this actually builds. In our main directory, let's make CMakeLists.txt. We will tell ESP-IDF to register this application as a component, and we will tell it where to find main.c, which is in this same directory, and any include directories, which we have none for this demo. Let's save that. I will add an extra new line here. Let's make another file. We will make CMakeLists.txt in the top level directory of our application. We will first specify the minimum required version of CMake, in this case 3.16, to align with everything else in ESP-IDF. We will then include that project.cmake file that's found in the IDF directory. That will enable all of the specialized ESP-IDF CMake tools for us to actually build this project. And we will give the project a name. In this case, we're just going to call it app. Save that file. Let's bring up a terminal. Let's go into apps and our I2C temperature demo. We're going to set our target to the ESP32 S3. Once that's done, let's call idf.py and build. With any luck, this should build our project. It looks like I've got an error here. I probably misspelled something. So if I control click on this, it takes me to where I need to go. It looks like I have a dot instead of an underscore. Let's save. It also says this was defined but not used, which means I probably misspelled it down here. Oh, I put 105.x. Ha, that's what I did. All right, let's save that and let's try to build again. It looks like it built, which means we're ready to flash. So bring up a terminal on your host machine outside of the container. Navigate to the repository that contains the apps that we've been working with. Activate the Python virtual environment and navigate into the I2C temperature demo folder. Make sure that your ESP32 device is actually plugged in so we can flash it. Then call python-m ESP tool, give it the port that's attached to your actual device. In this case, it's COM7 for me because I'm on Windows. Say chip auto to let it automatically figure out which variant we're using. Give it a baud rate to flash the device. Tell it to reset before and after flashing. Give it the actual command, in this case, write flash. We will say dual IO for the flash mode. Set it to 40 megahertz for the flash frequency. And we will set the flash size to auto detect. Then we give it hex 0 for the bootloader. In this case, this is for the S3 variant. Your variant might have a different location or address for that bootloader binary, so be careful with that. Then we will have hex 8000 for the partition table and hex 10000 for the actual application binary. Press enter, it should connect and hopefully flash to the device. Once that's done, we will call python-m serial.tools.miniterm, give it the port, in this case COM7 for me, and the baud rate 115/200. With any luck, it should restart and it should start printing temperature data to the console. Try lightly breathing on or lightly touching the sensor to impart some warmth, and you should see the temperature value rise and then slowly decrease after you're done touching or breathing on the sensor. If you go into the QEMU source code, you can find a hardware folder with some emulated sensors. There's a TMP105, which is very similar to our TMP102. Reading and writing to the TMP105 over I2C is the exact same, and it has the same registers. The configuration register is a lot simpler with only 8 bits, and it can only have 2 device addresses instead of the 4 found on the TMP102. By default, the address is still hex 48 with the A0 pin tied to ground. The one big difference we need to pay attention to is that the resolution is set to 9 bits by default. You'll either need to set the R1 and R0 bits in the configuration register to 1 to get all 12 bits, or be okay with losing some resolution. To keep things simple, I'll opt for low resolution. If you want to challenge yourself, try enabling 12-bit mode for this sensor. Here is the source code for the TMP105 that comes with the expressive fork of QEMU. If we scroll down, in addition to actually reading the temperature value using I2C, we also have these options to get the temperature and set the temperature from our QEMU console. And we can set the temperature using these units of 0.001 degrees centigrade or Celsius, in essence, millicelsius. Let's go back to our code here, and I'm going to zoom in a little bit so you can see what's going on. I'm going to set the target back to the default ESP32. That seems to work a little more nicely with QEMU, but you're welcome to try other variants. Next, I'm going to type idf.py QEMU. I'm not going to do monitor here because I want to be able to interact with the QEMU console so I can get and set that temperature. Give it a minute to compile and fire up the emulator. With some luck, you should see it restart the virtual chip, and it should start reading the temperature. Notice that the temperature is given at 25 degrees Celsius by default, but we're about to change that. Press Ctrl A and C to get the QEMU console, and let's type stop so that it stops flooding the terminal for us. This pauses the execution of the virtual ESP32. Notice that we are using the same code, and that's because the TMP102 and TMP105 have pretty much identical I2C communication protocols and register addresses. From here, there's a few commands we can use. Let's try info QOM tree. This lists out a tree of all of the hardware devices, virtual devices, that are connected to this instance of QEMU. And these are devices that Espressif have put in that we can work with and connect our virtual ESP32 to in order to try reading from or writing to various devices. In this case, there's memory, some GPIO. You can look through the various devices available here. This works like a tree. So it would start with this top one. So we'd have to call machine. And then there are some things attached to this ESP32 machine that you can see, including things like the CPU. There are fuses, GPIO. Here are our I2C buses. The buses should be communicating with one of these devices. So if we scroll down, we have this unattached device, and 26 is our TMP105. So we're going to use that path in order to communicate with this device outside of the virtual ESP32, but still within the QEMU environment. We're going to call this QOM-get function. Then we're going to give it that path. In this case, we're going to start with root. So /machine/unattached/device, and in brackets 26. That's that TMP105 that we saw. And then we can get a value. In this case, the name of that value is temperature. Think of this like a key value pair. So we're going to give it the key temperature. And when we run that, we see that it's set to 25,000, which equates to 25 degrees Celsius. And we also have this QOM-set in order to set values to these keys. In this case, we're going to set to the same machine unattached device 26, the same key, in this case, temperature. And now we give it a value. Let's try 15,000, which should set it to 15 degrees Celsius. In fact, we can QOM-get. Sure enough, that has been set for us. Then we're going to type out CONT, which is short for continue. We're going to press enter, and our virtual ESP32 is going to read from that virtual device, which has now been set to 15 degrees Celsius. This is how we can change our devices in QEMU in order to test things virtually before actually deploying it to a real hardware device. Or if you want to learn how to work with ESP-IDF and don't have access to a hardware device, this is incredibly helpful. Let's type stop so we get this terminal again. And from here, we can type quit to get out of our QEMU environment. I hope this helps you get started using I2C in ESP-IDF. Many sensors rely on this popular protocol, so this will be important as you build your IoT device using ESP32. If you enjoyed this video or found it useful, please click the like button. And if you want to learn more about writing firmware for IoT devices, I recommend checking out my online course. We start with the basics of ESP-IDF for writing professional code for the ESP32, then learn how to read from connected sensors and transmit that data over Wi-Fi using HTTP REST API calls to an IoT platform. We'll also tackle publish-subscribe mechanisms with MQTT before seeing how to secure everything using Transport Layer Security, or TLS. By the end of the course, you'll have the chance to build a full IoT sensor that publishes data to an MQTT broker, and you'll earn a digital certificate to showcase your new skills. Click on the link in the description to sign up.